Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be introducing electron configurations and orbital diagrams and help you to understand how to set both of those up. Let's get started. So electron configurations are really important to help us to map out where all the electrons are found within an atom. And so the ground state of an electron is the lowest energy orbital it can occupy. And these electrons are going to be distributed into various orbitals across the entire ground state of that atom. And this is what we call our electron configuration. Remember, when we're writing out the electron configuration, there's going to be a couple of components. The first thing is that there's going to be a number ahead of the orbital that's going to tell us what energy level are we in, or our N value. There will be a letter that tells us which orbital type are we in. Are we in an S, a P, a D, or an F? And then there's going to be a superscript value, which is going to tell us how many electrons are found within that sublevel. We can also create what are called orbital diagrams. Let me just move my box out of your way, move it out the way. And your orbital diagram is the same thing, but it's also helping us to understand the direction of our electrons within that orbital. Remember, we learned before that within an orbital, there can only be 2 electrons, and they have to be spinning opposite to one another. One would be going up and one would be going down. So it's important when you're thinking about how to develop your orbital diagrams, how many possible orbitals do you need to show per sublevel or per subshell. So with your S orbitals, you're only going to have one box or one line that you draw because there's only one type of S orbital that exists based off of those ML values that we've learned in chapter 7. For our P orbitals, well, there are 3 types of P orbitals that exist, and so we would show 3 lines. For our D orbitals, we learned there are 5 types of Ds that exist, so we would have 5 lines. And then for our F orbitals, there are 7 types of Fs, and so we would have 7 lines, 7 spaces where we can put our electrons. Remember, within each of these, we're only going to be putting 2 electrons per orbital that exists based off of the Pauli exclusion rule. So with orbital diagrams, your orbital is going to be shown one of 3 ways. Either it's completely empty, so there are no electrons found in it. It's half filled, meaning you have 1 electron, and you would put that as a half arrow designated in that upward position. Or it's completely filled, and that means you would have 2 electrons shown pointing in opposite directions because of those opposite spins. Now, as we're going about assigning and developing these electron configurations, there's a couple of things we need to keep in mind about how the orbitals are actually going to be filled. And so the sublevels in each principal energy shell of hydrogen all have the same energy. Remember, there's only that one sublevel that's found, that S orbital, so the same energy exists. So anything that's found at the same energy, we say those to be degenerate. Now, for multiple electron atoms, the energies of the sublevels can be split. And that's because you have so many electrons that are there that you get this repulsion phenomena that occurs. Now, the lower the value of the L quantum number, remember your L could be 0, 1, 2, 3, up to n-1, the less energy that a particular sublevel has. So S has less than P, which has less than D, which has less than F. Now, something we also have to keep in mind is that because there are so many electrons that are found within specific subshells, that you have this ability for the subshell to be able to penetrate into these higher energy levels despite being found in lower energy levels. So penetration causes the energies of sublevels in the same principal level to not be degenerate, meaning they won't be equivalent to one another. In the 4th and 5th principal levels, the effects of penetration become so important that the S orbital lies at lower energy than your D orbitals in the previous principal level. And same thing with our F orbitals, that really becomes more noticeable as we start thinking about where they're located. The energy separation between one set of orbitals and the next becomes smaller as you get beyond your 4s orbital. And the ordering can therefore be have some variation from elements. And so this is just going to help you to visually understand this idea of orbitals being able to penetrate into different sublevels. And so if we start with our first orbital that exists in our principal energy level, 1s, we know that there's only that s orbital that exists based off of those quantum numbers. And then on our second energy level, we now have s's and p's that are present. Now notice that p sublevel is higher than your s sublevel, and that's because there's more electrons there, greater amounts of energy. Our third energy level, we now have S's, P's, and D's. And so now you can see the hierarchy of the three. Well, now look at what happens when we add that fourth energy level into play. Move out of the way. When we look at that fourth energy level, now you can see that your 4s energy is actually at a slightly lower energy than your 3d because there's so many electrons there. And so that 3d is able to penetrate into that higher energy level. Similarly, as we add in our fifth and our sixth and our seventh, you can see that not only are the Ds able to penetrate into higher energy levels, but also those F orbitals are actually able to penetrate to higher energy levels. And so some things that we should be noting is that because of penetration, sublevels within an energy level are not degenerate, so they're not equal. And the penetration of the fourth and higher energy level is so strong that the S sublevel is lower in energy than the D sublevel of the previous energy level. And this difference really becomes noticeable as we get higher and higher. All right, and so now we think about how are we going to fill up these orbitals. We know that each orbital can only hold 2 electrons, but there's still a process that we have to undergo when we think about filling these. And so the energy shells fill from lowest to highest energy. So just remember that your sublevels from low to high are S to P to D to F. And that's what we know as the Aufbau principle. Now, orbitals that are in the same sublevel have the same energy. We want to remember that no orbital can have more than 2 electrons, and that's based off of the Pauli exclusion principle. And we also need to note that when we're filling up an orbital within a subshell, we have to give each orbital that's found there 1 electron first before we come back and make a pair. And this is what's known as Hund's rule. So what that means is if I have, let's take like a 2p orbital and I want to fill it up with electrons, I can't do this and make pairs like that. What I do instead is I give 1 electron to each orbital before I come back and make pairs within the orbitals, okay? And that's what Hund's rule is. And that's going to be important when we start doing our orbital diagrams shortly. Now, electron configurations in atoms in their ground state can be predicted based off of where an electron is found. And there's a lot of information we can glean from the actual electron configuration. And so if we look at the superscripts that are found within an electron configuration, well, if we add all those up, that's going to coincide with the total number of electrons that are found there. We can also predict things like, well, how many valence electrons are there? Or how many core electrons are there? Remember, we learned that the valence electrons are your outermost electrons, the highest energy level. Now, be careful when you're assigning valence electrons. It's not necessarily the last thing that you're writing, but instead it's the highest energy level. You have to identify, well, what's our highest energy level? And in this case, our highest energy level is 4. And so our valence shell is found here would mean we have 8 valence electrons. All right, and then with the remainder would be our core. And that should coincide with what we know. If you look at the periodic table, as we've done before, we know krypton is a group 8 element. So we would have always said there were 8 valence electrons, but this is just helping us to see the why. Now, we do have a shorthand way to be able to write these electron configurations, which is known as our noble gas configuration. And so what the noble gas configuration is saying is that this order that we're going to come up with is constant. We're going to be repetitive in what we're saying. And so if you want to write a shorthand version of electron configuration, you can simply write the noble gas that precedes or comes before that element first in brackets. And what that means is up until that point, the electron configuration is exactly the same. And then you add on the additional part that represents the remaining electron configuration. So if you look at this rubidium example, up from here, the beginning to here is exactly the same as what we see here for krypton. And so when you're writing the shorthand configuration, you simply write the noble gas that comes before it in brackets, followed by the remaining portion of the electron configuration. All right, so how do we go about filling our electron configurations out? I'm going to show you this method. I'm also going to show you one other method I like to use with my students that I found to work pretty effectively based off of how the electrons or the atoms are laid out on the periodic table. And so what the textbooks suggest that you do, you can actually come up and create your own map of the electron configuration order. And so what it's suggesting is you first start by writing down all the orbitals that are present or all the subshells that are present within any energy level. And so you can see for first energy level, we would have 1s. Then you move down a row and you write 2s and 2p's that exist. Then 3s, 3p, 3d, so forth. You write them all down. And then after you've done that, you're going to make a series of diagonal lines, and that's going to tell you how you're filling them up. And so if we add our diagonal lines, we see we go through the 1s orbital, then you can loop back around to the 2s, and then loop back around to 2p and to 3s and so forth. Now, many students like this method, and I do welcome you all to use this, but what I've found, if I've tried to draw something like this out, I may end up drawing things improperly or forgetting something. And so I run the risk of making an error in my assignment. And so I actually prefer using my periodic table to help guide me along the way. So if we look at a periodic table, that's what I have here, what I like to do is I actually write on here that over here, this first two columns represent my s orbitals. Over here, these 6 columns represent my p orbitals. In the middle represent my d's, and on the bottom represent my f's. And I also write down what energy level do these enter on. So in the corner here with my s's, I'm going to write the number 1 because in the first energy level, I have s orbitals. Over here by my p's, I'm going to write the number 2 because p orbitals enter on the second energy level. In the corner here where my d's are, I'm going to write the number 3 because that's where the d's enter. And on the bottom with the f's, I'll write the number 4 because that's where they enter. Now, when you're using this, you're just going to simply act like a typewriter and start from the beginning and talk about everything that you're passing through and reset back to the beginning. Bearing in mind that as you go down the row, the energy level will go up 1 respectively. So if we started at 1 here, this would be 1, 2, 3, 4, 5, 6, and 7. For the 2s, remember for the p's, remember we started at 2, so it'd be 2, 3, 4, 5, 6, 7. For your d's, remember those start at the third energy level. So we start at 3 here, we would have 4, 5, 6. And for your f's, we would start at 4, so it'd be 4 and 5. Now, if that method works for you, you essentially can create a map of every electron configuration that's possible just by using your periodic table. So use either method, you determine which way works best for you and run with it. And so what we're going to be able to do is actually write electron configurations for any atom and be able to make designations about how many electrons are present, what the orbital diagram would look like, and ultimately being able to assign quantum numbers for every electron. All right, so the things to remember before getting into these electron configurations, the group number is going to correspond to the number of valence electrons, just like we saw back in chapter 2, just like it's been doing. The number of columns in each block is the maximum number of electrons that the sublevel can hold. So remember, we talked about S's have 2, P's have 6, D's have 10, F's have 14. And then the period number corresponds to the principal energy level for that valence electron. And so here, this is what I was showing you a few seconds ago. This is kind of the layout that you want to remember. So over here are your S's. Again, that helium really sits right here when you're doing your counts. Over here are your P's. In the middle are your D's. And on the bottom are your F's. And if we write down the energy level that these start on, that'll help you to remember what energy level you're on as you're progressing through the electron configuration. Okay, be careful on looking at some of your periodic tables. Sometimes the lanthanum and actinide are found down here. So make sure if you see those down here, you do not count them in your F count, because that would give you 15. And we know that there's a maximum of 14 if we count the columns. So those are just the headers, the namings for those particular groups that are found there. So just make sure these are actually located in that D block. Okay. All right, so let's try some examples here. And so we want to get the electron configuration for phosphorus. And so what we're going to do is we're going to state every electron that we pass starting from the very beginning. So the first thing we end up going through is 1s. And how many columns do we have to pass? We have to go through 2. And that would put us at, again, helium is here, through helium. We then wrap around like a typewriter and go to here. And so now we would say that we have 2s and then 2 columns, so 2s2. Now we jump over and we don't say 1p because that's not where p's are introduced. Remember, we have that 2 there. We can now say 2p. And how many columns are we going through? 1, 2, 3, 4, 5, 6. So 2p6. Wrap back around like a typewriter. And we say 3s2, because we're now through that final column. Jump over. So if this was at 2, this must be 3. So we would say 3p3 for our phosphorus. All right, again, we can see how many valence electrons there are. Our highest energy level is 3. So in there we have S's and P's. So we have the number 5. We would have always said there were 5 valence electrons based off of it being group 5. Okay. All right, and so you can actually see here what they're showing you here is the noble gas configuration, the short configuration, that would also be suitable. Again, the reason we can say the noble gas configuration in that manner is simply because we're assuming that the electron configuration up until that point is exactly the same up to that noble gas, and then we can continue on. Okay. All right, let's try doing the electron configuration for arsenic. All right, so again, starting at the beginning, at the top, we start with 1s2, wrap back around, we're here, 2s2, jump over, then we have 2p6, wrap around, we're now here, 3s2, jump across. We're now at 3p all the way through to the end, 6, wrap around. We're now here at 4s2. Okay, now we're getting ready to enter this D block. And remember, the D block comes in at that 3rd energy level. So we don't say 4D, we say 3D, and we count the columns 10. And then we can go over to the next one, which is back up to the 4p3 for arsenic. Or if we wanted to write it as the noble gas configuration, we look at, well, what's the noble gas that comes before arsenic? And that would be argon. And then we can continue on with 4s2, 3d10, and 4p3. If we wanted to figure out the number of valence electrons, again, we do the same thing. Look at our highest energy level, which is 4, not the last thing that we're writing, highest energy level. So there would be 5 valence electrons, and we've always said 5 because it's in group 5. Okay. Okay, good deal. All right, so yeah, we've talked about valence electrons. And just remember that we can predict that based off of the highest principal energy level that's found. And our core electrons would be any and all electrons that are found outside of those valence electrons. And so the big thing that we want to remember with these valence electrons is that the valence electrons are what are going to dictate the behaviors of the atoms, both chemically and physically. And so it's because of that that we end up with elements that have very similar properties. And so if we look at some electron configurations here, we can see that for krypton, well, we would say that we have highest energy level is 4. So we have 8 valence electrons found there. If we looked at rubidium, the highest valence electron is found in the 5th energy level. So we would have 1. Okay. And so again, we can go through and assign these quantum numbers for any electron that's found in there based off of not necessarily the electron configuration, but the orbital diagram is what will really help you out in assigning those things. Okay, so we will get some practice here. And so here we want to write the full ground state orbital diagram and electron configuration for oxygen and figure out what the number of valence electrons and core electrons would be. So find oxygen. If you don't have your periodic tables, go ahead and grab them because you're going to need them as we're going through this. So if you find oxygen, as we do the electron configuration, we would start with 1s2, then proceed to 2s2. Then we jump across and say 2p4. For our orbital diagram, it would be 1s, one line. And again, we put our electrons up and down. We would say 2s, one line, up and down. And then 2p. Now we have 3 lines because there's 3 types of p's. And with those 4 electrons, when we put them in, remember Hund's rule, we have to give 1 to each. Then we come back and make a pair, okay? And so then if we're thinking about how many valence electrons we have, that would come from our outermost shell. So we would have a total of 6 valence electrons, and then we would have 2 core electrons. And you can note 6 plus 2 gives us 8, which is the total number of electrons that exist in an atom, okay? Again, you should be able to also, if you were asked to assign quantum numbers, let's just pick this one to assign some quantum numbers. We could say n is equal to 2 because we're in the 2nd energy level. L in this one would be equal to not 0 because we're not in the s orbital, but 1 because we're in the p orbital. Our ml values could be -1, 0, +1. And because we're in that 3rd position, we can just assign straight across. So we would say +1. And then our ms value, which is our spin, would be +1/2. Okay, so you can get a lot of information from these things. I know it doesn't ask this, but if you are curious about what the shorthand electron configuration would look like, well, you would find the noble gas that precedes it, which is He, and then you continue on with 2s2, 2p4 to show those remaining valence electrons. Okay. All right. Let's continue on. Next up, we're going to write the full ground state orbital diagram and electron configuration for calcium. So find calcium. So we would have 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. Our orbital diagram would be based just off of that. So we would say 1s with 1 orbital shown and my electrons up and down. Then we have 2s, orbital diagram, up and down. 2p, orbital diagram, up and down. So we go up, 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 down, 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 according to Hund's rule. 3s, 1 orbital, up and down. 3p, up, 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 down, down, down. Get in the habit of doing that because when it's necessary to do it, you'll be programmed to do that. And then 4s, up and down. For our valence electrons, we know it's the highest energy level, so that would be 4. So here we would have 2 valence electrons, which we've always said it's group 2. And for our core electrons, where there's a total of 20 electrons, so that means that we would have 18 core electrons that remain. If we wanted to write the noble gas configuration or the shorthand version, we would simply pick the noble gas that comes before it, which is argon, and then go on to 4s2. Okay. Great. Okay, here it says write the full orbital diagram and electron configuration for potassium. Well, it should look just like calcium, but minus 1 electron. So we would say 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Again, orbital diagram, 1s, 1 orbital, electrons up and down. 2s, 1 orbital, electrons up and down. 2p, 3 orbitals. And again, if you're struggling remembering how many orbitals each sublevel gets, find the section on the periodic table, take the number of columns that are there and divide by 2, and that'll tell you how many orbitals you need to do. So in the p subshell, we have 6 electrons, so we know that the number of orbitals has to be 3. When we add the electrons in, we go up, 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 down, 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 according to Hund's rule. 3s, 1 orbital, up and down. 3p, 3 orbitals, up, 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 down, down, down. And then 4s, 1 orbital, 1 electron. For our valence, we know it's going to come off that outermost shell, not necessarily the last thing we write, but the highest energy level. So we would say there's 1 valence electron and then 18 core electrons. Noble gas configuration would look like argon and then 4s1. Okay. Now, for our transition elements, we remember that those transition elements, those now incorporate those D block elements. And so remember, your Ds are actually going to be found at 1 energy level lower than your S's and your P's, but they're being filled in this order because of their ability to penetrate into that higher energy level. And so previously, we had not talked about valence electrons for our transition element. But now, if we look at it, we can think about what that number would be. Well, if in the transition elements, you're always going to have that s orbital that precedes your Ds and your Fs, that s orbital is what's going to dictate how many valence electrons that you have. And so you would typically have 2 valence electrons because your highest energy level is that s orbital that's found there. Okay, so remember, Ds will be 1 energy level less, Fs will be 2 energy levels less. Okay, and so here we want to write the full and ground state orbital diagram for manganese. So if we find manganese, we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now this is where it starts getting interesting. Remember, as we get ready to enter into that D block here, remember your Ds start at the 3rd energy level. That's where they're introduced. So you would say 3D, then count your columns over. Manganese is found in number 5, and so we would say 3D5. For our orbital diagrams, we would say 1s, 1 orbital, up and down. 2s, 1 orbital, up and down. 2p, 3 orbitals, up, 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 down, down, down. 3s, 1 orbital, up and down. 3p, 1 orbital, 3 orbitals, up, 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 down, down, down. 4s, 1 orbital, up and down. And then for your 3D, now we have 5 orbitals that we can fill, and each one will get an electron independently because of Hund's rule. In terms of valence electrons, we would look at our highest energy level, which in this case is 4. So we would have 2 valence electrons, and our core electrons would end up being 25 minus 2 or 23 core. You could add up all the other subscripts there. In regards to the noble gas configuration, we would pick our argon, followed and then continue on. So we would say 4s2, 3d5. Okay. And then last but not least, we will try uranium. And if you can do uranium, you can do any of them. Okay. So let's start at the beginning. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we go into the D's, so 3d10. Now when we get ready to come back up to our P's, your P's will be at the same energy level as your S's. So then it would be 4p6. Then we wrap around. So now we're at 5s2, 4d10. We're now at silver. Go into the P's, we would be 5p6, wrap around, and now we're at 6s2. Now this is where, again, things get a little interesting because we're going to start incorporating our f orbitals. So what we're going to first do before we get into the f's is we have to pass through that first part of the d orbital. So for initially, you may want to just note that we are going to go past 5d1. Then after we've gone through that 5d1, we now can jump down to our f orbitals, our SF subshell. So those start on the 4th energy level. And now we're going to pass all the way through the end and say 4f14. Well, now we return back to our Ds, and instead of saying 5d9 and separating out, or sometimes students may even think to say 5d10 here, you run the risk of forgetting about the fact that you already wrote 1d down. So the rule is, if you're going to be ending up passing through the F's and coming back to the D's, you're going to group all your D's together and just say 5d10 if you're going through to the end. You don't have to call out that singular d orbital electron. Now, if you are stopping in the F's, like you'll see when we get to the end of this, you do want to call that d out, okay? So we're at 5d10, and then we would go up to 6p6. We're now at radon, and then we continue on to 7s2. And again, now we're about to get ready to go back into those F's, but this time we do need to call out our 6d1 that we're going to pass through, because this time we're not returning back to the D's, and then state our F's, which would be 5f and 3. Okay. All right. So that was a long one. For our orbital diagram, same thing. So we would have 1s, 1 orbital, up and down. 2s, 1 orbital, up and down. 2p, 3 orbitals, up, 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 down, down, down. 3s, 1 orbital, up and down. 3p, 3 orbitals, up, 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 down, down, down. Again, this is according to Hund's rule. 4s, 1 orbital, up and down. 3d, 5 orbitals, up, 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 down, down, down. 4p, 3 orbitals, up, 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 down, down, down. 5s, 1 orbital, up and down. 4d10. So again, fill it all the way up, 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 then down, down, down. 5p, 3 orbitals, up, 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 down, down, down. 6s, almost done, up and down. Now for the F's, remember there's going to be 7 orbitals that we'll draw. And we give them the electron same way, up, up, up for all of them. Then come back and do our downs. We're running out of space here. Okay. And then we have our 5Ds, which again, we get 5 orbitals. And down, down, down. And then we have our 6p that are completely filled. And then we have 7s, 1 orbital, up and down. 6d, remember your Ds will have 5 different types of orbitals, but there's only that one electron there. And then last but not least, and I'll just put it over here, is our 5F, which has 7 orbitals. And we're going to fill that in with 3 electrons. Okay. In terms of our valence electrons, well, where are the valence electrons going to come from? They're going to come from our highest energy level, which our highest energy level is actually the 7. So there would be 2 valence electrons. And then the remaining would be our core. So we had 92 as the total number. And so we would have 90 core. If you can do this one, you should be able to do any electron configuration. I did just want to talk to you briefly about what the noble gas configuration would look like. So the shorthand or noble gas, if we look at the previous noble gas, we would say Rn. And then we continue on with the remaining portion. So then we could say 7s2, 6d1, 5f3. Okay, so a lot going on here, but hopefully you followed along. All right, so we're going to do a couple more examples and then we're going to conclude here. And so here we're going to be practicing writing our short electron configuration, a short orbital diagram. So if we find sodium, the noble gas that comes before it is neon. And then if we continue on, we would say 3s2. I'm sorry, we would just say 3s1 because it's only on that first column. For the orbital diagram, it would be neon, 3s, and 1, and we go up as so forth. For Te or tellurium, we would say krypton is the noble gas that comes before it. And then if we continue on, that would put us at 5s2, 4d10, and 5p4. For the orbital diagram, it would be same thing, krypton. But now we have 5s, 1 orbital, up and down, 4d, 5 orbitals, and we fill them all up, and then come back around, and then 5p. And we go up, 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 and come back down. And then last but not least, we have technetium. So the noble gas that comes before it is krypton, again. And so then we would say 5s2, 4d5. And for the noble gas or the orbital diagram, it would be 5s, 1 orbital, up and down. And then 4d with 5 orbitals and up, up, up. Okay. So again, a lot of information in this video. All right, the last thing I do want to point out in this video is some anomalies or things that might exist in some of these electronic configurations that you should be aware of. And so because of this sublevel splitting that occurs, we know that the S sublevel is technically lower in energy than our D sublevel. And so what happens is those S's tend to fill up before the D's. But the difference between energy is not really that grand. And so it makes it easy to be able to shift electrons between your S sublevel and your D sublevel because of that. And what ends up happening is for certain particular atoms that are out there, the electron configuration that you see are actually slightly different than what you would predict. And so some that you are going to see these anomalies exist are shown for you here. So if we look at chromium, which would have a shorthand version of AR, 4s, 2, 3d, 4. Well, because the S and the D are in so close proximity with the amount of energy that's associated with them, the 4s and the 3d, if we look at our orbital diagram for what's expected here, so we would have a 4s up, down, and 3d, and we have up, up, up. Well, what happens is in this case, especially in your D4 examples, is that this really isn't as stable as it could be. It could be much, sorry, that shouldn't be there just yet. It would be much more stable if that we had a completely filled or halfway filled sublevel. And so what's able to happen is you have a promotion of an electron from your 4s orbital that's given to this last d orbital, make all the d's look the same. That makes it much more stable. And so you're going to see this anomaly occur in your things that end in D4 and things that end in D9. And so what you really end up getting, your overall electron configuration is going to be slightly different. Same thing with our D9s. Same scenario. If we look here, we have 4s, again, up and down, 3D. In this case here, so we'll put a star where the promoted one is, we would start off with an electron configuration that's so close to being almost completely full. So to make it more stable, that electron from that s orbital is given to the d orbital because they're in close proximity to their energy levels to make this more stable. So what you end up seeing for your D4 or D9 is this promotion that occurs to help make your atom be more stable. And so same thing, this really applies to that entire column, your D4s, your D9s, and occasionally you'll see this with things that end in D6 or D8. But what you end up seeing is that you have that promotion that occurs of that electron to that d orbital. Okay, so just keep those in mind. Okay, I hope this video helped you guys understand electron configurations and how to work them out across the entire periodic table. Make sure you guys like, comment, and subscribe, and let me know what other additional content you would like to see. We'll be back with more videos in Chapter 8. See you guys later. Bye-bye.